Right. Okay, everyone, I'm really pleased to welcome you here to our last lecture of today after a nice long exam that I'm sure you all really enjoyed. So I'm really happy to welcome Dr. Clara Nellist here to speak with us this evening, who has worked on the ATLAS experiment in CERN, so has a great knowledge of particle physics firsthand, and also does a lot of science communication work, so is very well equipped to communicate it all to us. Over to you.
Okay. So hopefully you can hear me okay. Thank you very much for the kind introduction and thank you for being here. I realize I am the thing that stands between you and dinner. So we're going to dive right into this talk and hopefully there's still time for questions afterwards. And if not, you can always come and find me during the dinner or tomorrow. So let's see. So the title of my talk is From Hydrogen to Higgs Bosons. But also in the history of the universe, we could go from Higgs bosons to hydrogen. But today we're going to talk about the Large Hadron Collider at CERN. So, this is where I work. This is it on a good day. Sometimes we get lots of rain, but sometimes it's also sunny. So this is the CERN site, and I don't know if I have a pointer, but my experiment is over there on your right, and my office is somewhere over on your left as well. So this is the Mehran campus. But first, I just want to say a little bit more about who am I and why I'm here. So as I said in the introduction, I'm a particle physicist. So I got my PhD from the University of Manchester. It's also where I did my undergraduate. And then I did my PhD working on the ATLAS pixel detector. So I'm going to tell you more about what that means. So it was a very hands-on PhD, and now I've moved more to the analysis side, so I analyze the data from the experiment. But on top of that, I'm also a science communicator, so you can find me basically on any platform. I'm not on Twitch, but most of the other platforms you can find me on. So if you have any other questions after this, you can also find me there. If you want to ask about career advice or your favorite particle, that kind of thing, then feel free to message me. So I make videos mostly online about the physics that we do at CERN to explain the research to everybody. So let's dive into what are we actually looking for with the Large Hadron Collider. Now this equation basically describes the building blocks of the universe, but I'm an experimentalist, so we're not going to dive into this. I just wanted to put it up. It's the only equation that we have in the whole talk. But if you're a theorist, then this is the language that you talk with. But for me, I talk with the data and the hardware that we have at the LHC. So my job is to study nature's building blocks. So we want to know what are the smallest building blocks in our universe, how do they interact with each other, how do they evolve over time. And there's a really nice collaboration with cosmology, because cosmologists and astrophysicists, I think if I go too far away from the mic you can't hear me, so I stay over here. They use telescopes to look out into our universe, and this allows us to also look back in time. So the further out in our universe we look, the further in the history of the universe that we're studying. But with particle accelerators and particle colliders, we use our equipment to recreate the conditions in the early universe. So we can, for very short instances, recreate what those conditions were, and then study how they evolve and how these particles interact with each other. And what we're doing is not anything particularly unique for the universe, but it is unique for humans. So there are higher energy collisions elsewhere in the universe when particles collide with our atmosphere and in other instances as well. We're doing it in a very controlled way in order to be able to study what happens with our detectors. So I want to preface, before I go into the details of this is a slightly historical view first. So we're looking at what did our recipe book of the universe look like before we turned the Large Hadron Collider on. So this is before we discovered anything new, if you want some spoilers. So this is our recipe book. It's a bit similar to the periodic table that we have in chemistry. So this is the particles that we have in the standard model. There's some structure here that I won't go into too much detail of, but it's what we study as part of our research. So we have the fermions on your left. These are the matter particles, the stuff essentially. And some of those will be really familiar, like the electron and perhaps the up and down quarks. And then we have 3 generations of them. And one of the big questions in physics is we don't know why there are 3 generations. We just know that there are. And we also have neutrinos, which are really interesting particles to study. We can't study them too much with the Large Hadron Collider, but there are many other fantastic experiments around the world that are really studying these particles in a lot of detail. And then on the right, we have the force particles, the bosons. And so each of these are part of a particular force. So the one that's perhaps most familiar to you is the photon. And this is the particle that is part of the electroweak force, the electromagnetic force, sorry. And then we have the Z and the W boson. And these bosons are essential for having the sunshine. Without them, we wouldn't have our sunshine. And the gluons are the particles from the strong force, and these really hold both the inner part of the nucleus of atoms together and also the protons and neutrons themselves together. So these are really important particles that we study to understand how our universe works. But there are some big questions, things that are missing, and as I remind you, this is a historical perspective before the Large Hadron Collider turned on. So at the moment, there's no Higgs boson in this recipe book. There's also no dark matter or dark energy, and I'll explain a bit more about those just in case in a minute. And since I was talking about forces, you might notice one that we're really familiar with every day that's missing, which is gravity. There's no graviton in this recipe book. So let's dive into these big questions a bit more. So here are just some pictorial representations of those big questions. And the first one I'm going to talk about is the Higgs boson, because this was discussed a lot when we constructed the Large Hadron Collider. It was proposed around 60 years ago by a number of theorists, 6 in total, and it was proposed as a mechanism to give mass to elementary particles. So things like electrons, how do they get their mass? And the physics of it is that we have this expectation value, so this vacuum value for the Higgs field, which is throughout the whole universe. And our understanding in theory is that it started off at 0 in the very early stages of the universe. And then some mechanism, some evolution of the universe happened to cause that value to go down into a lower state. And so it's off the center. So you see this nice cartoon on the right. It's off the center in its properties. This is just a value of its property. And when it's off center, then it gives mass to particles. By interacting with this field, particles get mass. But to give you a bit of a better idea of what... and just I wanted to say a nice fun fact. If this happened very quickly, there's 2 ways that this could happen. This value could change gently over time in the early universe. Or this, you see this ball, if it rolls down the hill very suddenly, then what you get is suddenly all the particles have mass, and you get ripples in this fabric of our universe, which could cause gravitational waves. And so there are some really nice studies, some nice suggestions that with even more sensitive gravitational waves detectors in the future, perhaps we could even detect this ripple of this property changing in our universe. This is very far into the future, but it's kind of cool that you could maybe see echoes of this happening in our universe. Okay, so hopefully we don't get the sound here, but I want to show you a bit of a better explanation of what that means for the Higgs field, because sometimes it's better to view things visually. So here are some videos of me in a field of snow, and the field of snow here represents the Higgs field. So the Higgs field is everywhere in our universe, and so I want you to imagine it like a field of snow. And so if you have a light particle, so here this is like an electron, if it's interacting with the field very lightly, it is interacting, but not very much, then this is a light particle. So it's like somebody being on skis and being able to very easily move through the field, but there is still some interaction. Whereas if we have a heavy particle, it doesn't have skis anymore, and it's interacting a lot more intensely with the Higgs field, and therefore it's more massive. And so the more that a particle interacts with the field, the more massive that it is. And then if you have a field of snow, but you can't see it, but you find a snowball, then you can infer that the field is there. And so what we were looking for with the Large Hadron Collider is snowballs. We were looking for evidence of snow to know that this field existed. And so that was the big achievement, that's the spoiler for later on in the talk, of being able to say that this field existed. Okay. So one of the big challenges is, though, so we're looking for these snowballs, which are the particle that we want to say proves that the Higgs field exists. But that equation that I showed you at the very beginning of this talk, it has the prediction for, or it doesn't have the prediction of the Higgs field. It had to be added in. But it doesn't tell us what mass the particle should be at. So it predicts that there should be a particle, but we had no idea what mass that Higgs particle should have. And so here are some graphs. On the left, we're looking at how often these Higgs bosons should be produced in the Large Hadron Collider. And on the right, we're looking at how often it should change into different particles. And you can see all these lines change depending on the mass on the bottom of the plot, which means we don't actually, it's very difficult to know what to look for. If you have a very light Higgs boson, then it's changing into, hold on one second. Yeah, no, that's right. I got confused with taus and top quarks. If you have a very light Higgs boson, then it's changing into these particles on the left very frequently. But if you have a heavy Higgs boson, it's much more likely to change into the heavier particles. So we had to look in all directions, in all different types of decays, of changes of this particle, in order to be able to discover it. Okay, so that's a little bit of the theory behind the Higgs field. We're also looking for dark matter and dark energy. So something that's really interesting in physics, especially particle physics, is that we only actually understand about 5% of our universe. 5% of, and not even fully, 5% of our universe is visible matter. It's the, those particles that I showed in the standard model at the beginning. The rest of the matter and energy in our universe is dark matter and dark energy. And most of it is dark energy. So dark energy is the thing that is causing the accelerated expansion of our universe, which was a very surprising discovery in the history of physics. And we don't understand why this acceleration is happening. So we give it a term, dark energy, and we just we call it dark when we don't really know what's going on. And dark matter is a very interesting substance because we know something exists in our universe. We see direct observation of a lot of matter in our universe that we can't see. We see the effect of it, but we don't see it visually. So what you have here on the left is a galaxy in the middle of the picture and a galaxy at the very far left. And what happens, Einstein showed, that very, very massive objects warp space-time, and so even light gets its path bent on its way towards us. And we can measure how much visual mass is in the galaxy in the middle from our observations, and we can measure how much the light is distorted, and these two numbers don't match up. So this is one clear observation of dark matter, that there is more stuff in our universe than we observe, but we don't know what it is. We have no idea. We have a few hypotheses, and we can look at the effects and the evolution of the universe, but we don't know what it is. And I will admit a bias right now. I'm a particle physicist. I think it's a particle. But if you ask someone who studies modified gravity, they think it's modified gravity. If you ask someone, well, not everybody, but people will tend to think it is the thing they study because that's why they study it. So you're listening to a particle physicist, so you're getting a very biased particle physicist's assumption. But if it is a particle, then there are lots of things it can be. So here in the middle, in this white circle, are the visible matter that we have in our universe. And on the outside are the proposals for what dark matter could be. And there is no reason that it only has to be one of these things. Just like the visible matter is made up of a lot of different types of particles, dark matter could also be made up of a lot of different types of things. And really, we would love to find evidence of any of these, because then we can start pulling the thread of what dark matter is and understanding more about its properties. And some of these hypotheses are either particles that are produced with the Large Hadron Collider or have some effect on our measurements with the Large Hadron Collider. So this is why we're studying it and I'm interested. There was a really nice, or is a really nice proposal called supersymmetry. And in the early days of the Large Hadron Collider, people were very excited about this proposal. I don't have time to go too much in detail, but essentially all these little particles, the cartoons of which you see on the left, are the standard model ones that I showed you in that diagram. And in supersymmetry, they have more massive partners, which all have funny names because physicists are not very good at naming things. And so it's a beautiful theory. It explains so much, but we didn't find any evidence for it so far. And again, another bias, I am very much an experimental physicist. I think theoretical physics is super important. Some of my best friends are theoretical physicists. But if we can't find evidence for it, I'm really sorry, but that's not how the universe is. So it's not ruled out completely, but it's being pushed further and further back into more complicated versions of supersymmetry. So we're still looking for it, but now we're also broadening our search. What else could it be? How else could it show up in our measurements? We use machine learning to look for what we call model-independent versions of new particles. So we don't rely on one theory, but we just look for anything weird in our data that could show up. So this is one proposal, but sadly, so far we haven't found any evidence for it. Another big question in our universe is the difference between matter and antimatter, and essentially, why are we here, and why didn't we just annihilate with all of the antimatter in the early universe? So we believe that in the very early universe, there were equal amounts of matter and antimatter, and when they meet each other, they annihilate. So why did a very tiny amount of matter get left over in order that everything that we see, our planet and most of the things we see out in the universe, are made of matter? So this is a big question. It's mostly searched for by one of the other experiments on the Large Hadron Collider that I don't work on. But it is a big question in physics. And I always love to leave this picture on the right up because it is the first photograph of antimatter. And it's a beautifully simple measurement, but it was the first discovery of a positron, which is an anti-electron coming into the frame, and the lead strip in the middle slows the particle down. You have a magnetic field. You can see that something with the mass of an electron has been observed in this experiment, but it's bending the wrong way. It has the wrong charge. And this was the first discovery of antimatter. Okay, and then I also mentioned gravity. So we're very aware of gravity every day. If I fall down a flight of stairs, it will hurt very much. But actually, it's an incredibly weak force. I can overcome it easily by lifting this bottle of water up. So it is an incredibly weak force, and we don't understand why. And also, so far, we've discovered no particle that is associated to it. So it is a big question in physics. We do look for the graviton, but it's not our main area of research. It's not something that we particularly focus on in detail. But still, it's a big question. So is there a graviton? Some of the ways that it could show up is that there could be extra dimensions, for example, in string theory. And then gravity could be leaking into these additional dimensions, and that could explain why it's so weak. And another big question that I'll touch on near to the end is, what is the strength of gravity for antimatter? So when we're looking for the difference between matter and antimatter, the fundamental properties, how do they differ, or are they the same for these two types of matter? So how do we go about answering these questions? These are some of the big questions in particle physics that I've introduced. But how do we go and test them? Not me personally, I mean in this lecture. Otherwise I'd be getting some prizes in Sweden. Okay, so as I mentioned, I work at CERN, so I work on the Large Hadron Collider. So in case you're not aware, CERN is the nuclear research site in Geneva, and it's located here on the border between France and Switzerland. That's Lake Geneva on the right. Down in your bottom right is the airport, just to give you a sense of scale. And the accelerator is 27 kilometers long in a big circle. It's about the size of the Circle Line in London, the metro, if anybody has been on that Circle Line in London. We have 4 main experiments on the ring. We have ATLAS and CMS, which are general purpose detectors. We basically measure everything that we possibly can and try to understand it. We have LHCb that I briefly mentioned. They're focusing more on this question of matter and antimatter asymmetry. And they want to look at questions of exotic types of matter, new ways that quarks, for example, can combine together. And then we have ALICE, and they study heavy ion collisions. So we don't only collide protons in the Large Hadron Collider, but we also collide heavy ions. And this is where we recreate those conditions in the early universe, because we're colliding very massive ions together, and they create this soup of quarks and gluons in their collisions, which we believe is similar to the conditions in the very early universe. This is the accelerator complex. So mostly when you hear people talk about CERN at the moment, we talk about the Large Hadron Collider, but is actually only the very end of the accelerator chain. So we have a number of accelerators that have been built since the 1950s. Some of them are still running. And we make use of the infrastructure as we add new technology onto the site. So we're not starting from scratch every single time. We want to be frugal with the money that we have. And so we build onto our existing infrastructure. And also, again, another bias. I work on the ATLAS experiment. I'm going to be talking mostly about Large Hadron Collider research. There's other fantastic research going on at CERN. So, for example, Isolde, which is over to the right, is studying nuclear physics and exotic forms of atoms. And we also have, I'm going to talk a little bit about our antimatter research, but mostly I focus just on the ATLAS experiment. So now we're going to look at how the title of the talk essentially, so how do we get our Higgs bosons? So we do, let's see if I can, oh no, this is going to go wrong. Let's start this again. Okay, I'm just going to have to talk very quick because I can't pause as we go. Okay. There we go. Okay, brilliant. Okay, so I'm just going to talk over the video and it's not going to pause for me. So we start with a bottle of hydrogen, genuinely just a bottle of hydrogen. This gets fed into my favorite thing called the duoplasmatron. And the electrons, originally the electrons were stripped from the hydrogen. Now we add extra electrons on, focus the beam, and then strip them away. And then what's happening is our protons are going through a number of different accelerators that you're seeing in this video. So we start with the we started with the linear accelerator, then we have the proton synchrotron, and this is then fed into the next series of accelerators. So we have the super proton synchrotron. I think we missed one because the video went too quickly. But what's happening is at each stage, the protons are getting accelerated even faster, and we're also collecting them in bunches and then in trains. You can literally think of like a train where you have different carriages, and this is how the protons are collected together. There are 100 billion protons in each bunch in the Large Hadron Collider when we're at high intensity, and then we collide them together in the center of our experiments. This is an incredibly technical procedure. It's also an area of intense research. There are accelerator physicists who dedicate their research to making the accelerator more efficient. In order to focus these beams, we use dipole magnets to bend them around the Large Hadron Collider, and we use higher order magnets to focus them together. So like quadrupoles and sextupoles and octupoles, all of these higher order magnets make that bunch of protons more compact. We have features called collimators, which strip the protons that are drifting away so that they're even more tidy for the collision. So it's an incredibly technical procedure just to get from that bottle of hydrogen to the collisions in the center of the detector. And then that's where people like me step in, because I work on the detectors themselves. So the accelerator folks have provided the collisions, and then we build essentially a giant camera around this collision point, and we're studying what comes from those collisions. So just one comment on the protons themselves before we move on. Protons are actually very messy. I would prefer not to collide protons because they are not fundamental particles. They have quarks inside of them, these big blobs, and they have gluons, which are holding them together. And then there's also actually a whole sea of other quarks and stuff floating around in them. They're incredibly messy particles. And so when they collide, we don't know exactly which bit of them collide, and we don't know which part of their energy. So when we talk about the energy of the protons, that's the maximum energy, but it's not the actual energy of the collisions. But because protons are more massive than electrons, essentially for our accelerators, it means we can accelerate them more. So with the electrons, which are very clean things to collide, because they're so light, they give off synchrotron radiation. They kick off a whole bunch of radiation every time we change their direction. And so as you change them around a tunnel, they're kicking off and losing energy, and it makes it very inefficient. This is one of the reasons we build our accelerators bigger and bigger, because the bigger circle you have, the smaller the turning radius, and so the less energy that's lost as you send them around the ring. But getting a very large tunnel is a complicated procedure, so we also try to be as efficient as possible. So by using heavier particles, we can get to higher energies in the same tunnel. So we started off in the same tunnel for the Large Hadron Collider, colliding electron-positrons, and now we collide protons. And this plot that I'm showing on the right is just showing the number of collisions every time those 100 billion protons cross each other. We get on average about 60 collisions at the beginning. So from 100 billion to 60 collisions each time they cross. But this is still very complicated and a big challenge for our detectors, because each of those collisions, some particle is formed from the collision, and then they very quickly change into other particles, spray things off, and it becomes our detector lights up, and it becomes a big challenge being able to read everything out. Okay, so now I want to talk about the detectors. This is my favorite thing because it's what I work on. So as I said, we have 4 main experiments, and I'm the one on the bottom right. So this is the ATLAS experiment, and it's one of these general purpose detectors. We try to measure as much as possible from the collisions and then see what comes off. So I have another nice video made by the CERN communication department showing these collisions. So as I said, we have these bunches of protons. There's about 2,000 of them in the LHC, and each time the bunches cross in our detector, we get collisions. And for example, if a Higgs boson is created, it doesn't last for very long at all. We've never measured a Higgs boson in our detector ever. We measure the remnants, the decay particles from the Higgs boson. And this also makes it a challenge, because you then have to know, what does your particle change into? How often does that happen? How did those particles show up in your detector? Are there things that can fake that signal? So it's a big, technologically challenging procedure, and that's why there's thousands of us working together. So this is my experiment in sketch form. This is the one I used in my PhD thesis, and I got to sneak an extra feature in to the image. I thought the people weren't big enough to show how big the detector was. So this is actually, it's Sue, the T-Rex from the New York Museum. So it's to scale. I made sure that I measured it. And what I want to show you really with this is just how giant the detector is. It is 44 meters long, and it's 25 meters tall. And we have many different custom-made components that have a different job inside the detector. So as I said, all these particles come off from the center, and we need to identify what they are. So the job of each bit of our detector is to learn something unique about each particle. How does an electron show up in the detector? How does a muon show up? What are the differences, and how can we tell them apart, essentially? To give you an idea of, again, the scale, so this picture is from 2002. It is an empty cavern before we started constructing the ATLAS experiment. And then you might think, how did you get it down there? So what I didn't mention actually before now is that this experiment is 100 meters underground. So we need to get all of that detector 100 meters underground. And if anyone's ever had the hobby or knows someone of the hobby of building ships in a bottle, then you might wonder how the ship gets in through that narrow opening. That's exactly how we built the ATLAS experiment. So we have a number of shafts. We have 3 shafts to the surface. And we lowered each piece of the detector that was built. Everything was built around the world, and then it came together, constructed into larger pieces, which are then lowered into the cavern in order to construct the ATLAS experiment. And this is what we get at the end of that. So this is a fisheye lens photograph that I took of the experiment, and I had to stitch all these pictures together so that we could get a good view of the detector. The ATLAS experiment is so big that you can't actually stand anywhere in the cavern and see all of it. Whenever you go underground and you get there, you're immediately in front of the detector. Some of the other experiments have nicer viewing platforms, so I'm very envious of the way that you can see those detectors, but ours, we really filled the whole available space of the cavern. And just to give you an idea of how massive it is, those are people at the very center of the image of the detector. It's really a huge experiment, and it's because the particles have such high energy, we need to build all of this material in order to stop them and get the information that we need. And I really want to emphasize again how many people are working on the experiment, because you see me right now, I'm just one of 5,000 people on my experiment. There are 5,000 people on the ATLAS experiment. About 3,500 of them get to sign the papers because they've done some sort of service to the collaboration, which means you can sign the scientific papers. And we have over 100 nationalities in our experiment. So it's a truly international endeavor. And to give you another sense of that, I've grabbed photos of the different collaborations. So mine is down here on the left, and we have the accelerator physicists in the center at the top. And I would estimate this is maybe about 5 to 10% of the people working at CERN. It's not even, we have no photograph of everybody. In fact, I know that this year is the 70th anniversary of CERN, and they want to try and get as many people as possible together for the anniversary, and we're still not going to get everybody in a photograph. So it's truly a big endeavor. And so this animation now is to give you a little bit of a better idea of how we measure those particles and how we get the unique identification of how they work. So there are 3 main parts of our detector. So to explain what this picture is, you are sat on the Large Hadron Collider right now. So we have the pipe going into the screen. You're sat on it. You're looking at the detector head on. Okay? And so particles are collided in the center, and they're going to come off in all directions. And ideally, they're going to sort of go up and down in the screen. And this is just a slice of the detector. And we have a section of it very close to the collision point, which is called the tracking detector. So we're tracking the charged particles where they go inside of our detector, charged particles like electrons. Then we have the calorimeter, this brown and blue section. So they both have slightly different jobs, but the calorimeter is to measure the energy of particles. And we can only do that in a destructive way. We have to stop them and get them to deposit their energy in our detector, and we measure that out as an electrical signal. And the best way to remember the name of the calorimeter is to think of the word calories. So calories tells you how much energy you get from your food. The calorimeter tells us how much energy we get from our particles. And at the very end, we have the muon spectrometer. And muons are very interesting particles. They're the heavier cousins of electrons. And they travel through many, many layers of stuff before they eventually give up their energy and stop. And that's why when we have cosmic rays, we have particles coming from space that collide with our atmosphere, the main thing that makes it down to the surface are muons. And it's also one of the reasons our detector is 100 meters underground, and that's to try and protect it from some of the cosmic rays, some of the muons. There's a number of other reasons it's underground too. We don't protect it from all of the muons, and we actually then use that to our advantage because it helps us to calibrate our detector. When you've got a lot of straight lines passing through your detector, it helps you to work out where everything is. But ideally, when we're doing our measurements, we have to remove those muons from our data set. Okay, so we're going to look... oh, there we go, perfect. I didn't want to press the button again. So we have an electron, and it's passing through our detector, and it passes through the tracking detector and deposits its energy in the calorimeter. We also have a photon, which just deposits its energy in the electromagnetic calorimeter, a photon, and then we have a proton, which makes its all the way out to the hadronic calorimeter. Now, I won't go through every single particle, but what you'll notice is each one has a different signal in this detector. So we are able to start distinguishing between them. And this dotted line that you're seeing coming out now is the neutrino, and the neutrinos we cannot measure with our detector. So we infer that they were there from the conservation of momentum. We have to do some calculations, but otherwise we can't measure them. There is a really nice experiment called PHASER, which was built down the beam pipe and has done the first measurements of neutrinos from a collider, but we can't use that data to connect it to a specific event. They just collect a number of them. Okay, I'm going to skip this animation so that we can get to dinner quicker, but what it's showing, and I can send it to anybody who wants to see it later, is essentially that we have a lot of data. We have petabytes of data coming from our collisions, and so we cannot keep it all, and we have custom hardware and software that makes decisions on which data to keep. And this is a big area of research called the triggering. It's the data selection or data acquisition, and we have to make the right decision, because if we throw away a piece of information, we can never get it back again. It's lost forever, and we have to redo all of our collisions. But I'm going to skip it just for time. Okay, so this is kind of a historical perspective. So we're now at 2008, and we have the first beams in the Large Hadron Collider, which was an incredibly exciting moment, and you can see the control room is pretty full of people. And this is what they were really excited to see. They cheered when this plot on the right showed up. And it looks very simple, but what it shows is one of those dots is a bunch of protons leaving at one point of the LHC. And that bunch went 27 kilometers around the ring and showed up at the other end, showed up in the same place again. And so it was the first time that a bunch of protons had gone all the way around. And this was exciting, and PhD students were finally going to get some data from the collisions. And then, very sadly, we had a magnetic quench. And I can't go too much into detail about the magnets, but they're super interesting. But essentially, they are superconducting, our dipole magnets in the Large Hadron Collider, which means we cool them down to 1.9 Kelvin, and then they have no electrical resistance in them. Then we can put 12,000 amps through the wires of this dipole to create 8 Tesla magnetic fields to bend those incredibly highly energetic protons around. But if the temperature goes even a micro degree too high, they lose their superconducting properties. We call it a quench. And unfortunately for this magnet, there was one solder connection that just wasn't done correctly. It created a tiny spark, a tiny amount of heat, which was enough to switch off the superconducting property. And then you've got 12,000 amps going through a regular cable. That resistance was enough to knock the magnet out of place. And unfortunately, this set us back an entire year because we had to warm up the whole cavern, remove this magnet, reinstall a new one, cool it back down again, check every single solder connection, and then what we call train. We have to train these magnets, which takes many weeks and months in order to get them to be able to withstand that amount of current going through them. But we did it, and in 2009 we had the first collisions in our detectors, which was incredibly exciting. And from this moment on, we start collecting data. And the crunch is on because the Large Hadron Collider promised it would either find the Higgs boson or rule it out completely. This was the last accelerator that was needed for this particle. And so both the ATLAS and CMS teams were in a race to see who could get there first. Oh, and before we got there, the LHC became the highest energy particle accelerator in the world, and the previous accelerator, the Tevatron at Fermilab in the US, they had a conference where all the accelerator physicists met, and they handed over the baton for the highest accelerator, which I thought was a very nice touch, and it's in the CERN control center to show. And I hope that when the next accelerator is built, we carry on the tradition and hand over to the next team. And then 2012, as I said, we were collecting the data. So this is the ATLAS experiment. We're looking at 2 photons. We're combining the mass of them together, the momentum of them together. And you can see that, well, we expect it to fall as it increases in a nice slope, but there's a little bump that forms at a specific mass. And it's not a very big bump, but this was incredibly exciting. People lost sleep over creating this plot. And then CMS did the same thing, and we looked in a number of other different, we call them channels, different ways that the particles show up in the detector, and we started to see a lot of stuff at 125 GeV, the mass range that we look at. And this led to this moment, which is the auditorium at CERN, where ATLAS and CMS in 2012 came together, gave joint presentations. I said there was a race, but we got there at the same time. And the world watched as this announcement was made, and we announced we had a brand new particle. At this time, I was a PhD student, and I'm right at the back of this image. So this is the front page of the New York Times. You get to be on the front page of the New York Times if you discover a brand new particle. And that's my face. I was in the room, which is one of the most incredible meetings I've ever been to, and I've been to a lot of meetings. And to get there, I slept outside of the auditorium with my friends. We turned up at midnight the night before, which I'm very grateful. I don't remember who said that we should do that, but I was just going to rock up at like 6 a.m. the morning of the meeting to try and get a seat in the auditorium, and my friend said, no, if you want to be there, you got to be there the night before. And so we were the second or the third group of people outside of the door. We had Disney movies and blankets and popcorn, and we stayed up all night, and we got into the auditorium, and then we watched the presentations. And so this was the spokesperson of my experiment, who is now the Director General of the entire CERN site, Fabiola Gianotti, as she was giving the presentation to say that ATLAS had discovered this new particle and that we were confident it was something new. And it was a very emotional day, and hymns was had, and it was fun. Okay, so now I can show you the standard model now with the Higgs boson added to it. So it might just seem like one additional new particle, but it was an incredibly important advancement for our understanding. It's the first scalar boson that we've ever discovered. It has a different quantum spin property to the other bosons that we have, and it tells us how elementary particles have mass, which we did not know before we've measured this. Okay. But it's not the end of the road, and there are more things that we are trying to measure. So I'm going to whiz through some of the other things that we're looking for, because one of the big questions I always get now at CERN is, okay, you've discovered the Higgs boson, job done, time to go home, which is not true. We are searching for new particles, and this graph is a little bit complicated. I don't want to spend the time going through everything, so I sketched it. So on the left, we have all the different types of new particles that have been proposed that we're looking for in our experiment, and the different ways that we looked for them. And then the orange and yellow lines on the right are us ruling out those particles. So the further along a line is, the more massive it needs to be to still exist. Otherwise, it's been ruled out and it doesn't exist. And all I really want to show you with this is there are lots of them. There are lots of theories, and it's kind of a bit like tennis. We keep batting them back to the theorists and saying, thanks very much, but sorry, not in our detector. So we keep measuring and trying to look for these new particles, but they're not showing up. But this is a big part of particle physics, and saying that things don't exist is an important discovery. Each one of these is a paper, which is setting limits on at what point this particle could still show up at if it does exist, which tells the theorists more information about our universe. But it's not just about discovering new particles. We have a whole bunch of particles, especially the Higgs boson, that we want to know more about. So this is a bunch of the different measurements that we're doing called precision measurements. This y-axis is 15 orders of magnitude in scale. So it's a whole bunch of very common things on the left that show up in our detector, and very rare things on the right that are very difficult to measure. And so these are all the measurements we've done, and we compare them to theoretical predictions. And each one of these is a team of sort of 30 people, or 10 to 30 people who are doing these measurements. So it's a very complicated procedure, and we need to compare not only does our measurement show up the same as the theorists predict it, because then we're confirming what the theorists have said, but also, if there's any difference, that feeds information back in that maybe the theorist's calculation needs to be updated, or maybe something else is going, maybe there's another particle in there, there's a new force, that kind of thing. So these precision measurements allow us to really look at the details of the calculations. And one in particular is the precision Higgs measurement. So we do a lot of different measurements of the Higgs mass. And it's a really important measurement because we want to know if our universe is stable. So when I showed you at the very beginning of this talk, when that ball rolled down the hill and it was the quantum property of the Higgs field, it could be that that's not the only place it could land. It could be one minima, and it's possible that there's another one further away from the center, essentially. And that's what we would call an unstable universe. And if that's the case, and the property quantum tunnels, then all of the laws in our universe change in an instant. This bubble ripples out at the speed of light from wherever it started, and let's just say life as we know it wouldn't exist. Fortunately, so far it looks like we're in what's called a metastable universe, which means this is incredibly unlikely to happen on the lifetime of our universe. And if, for example, dark matter is a particle and it interacts with the Higgs field, it would change where we are in this graph, and that could also push us into the stable region. I mean, we know our universe is pretty stable because for the last 13 billion years it's existed, but it's kind of nice to know where we are on this graph. So it's a really important measurement to make, and I just want to really clarify that measuring the Higgs boson has absolutely no effect on this likelihood to happen. As I said, there are higher energy collisions elsewhere in the universe, and so we don't have to worry that by running the LHC we're going to cause this to happen. It's purely for curiosity. Okay, so I'm going to skip this one, but we're measuring the interaction of particles with the Higgs field, and perhaps dark matter in the top right shows up somewhere as well, which would be very interesting. And yeah, as I said, and we want to measure the Higgs interacting with itself because it tells us more about the angles of these lines, and we can project them to see how stable our universe is. Okay, one quick interlude, and then I wrap up with some small points. So one side note I wanted to mention is that on the 29th of April 2016, the Large Hadron Collider experienced a power cut due to a short circuit. And the cause for this, you may have seen it in the news, you might have not, but it's what we call a pine marten. And I just want to really specify this image is for illustrative purposes. It's just to explain what happened. Also, it wasn't running around in the tunnel. It chewed a power cable outside of the site. But this didn't just happen once. It happened twice in the lifetime of the LHC. And the reason that I mention this is because we're doing these grand searches, and it's the most complicated equipment that we've ever built, and we protect it as much as possible. But sometimes you can't help a pine marten or a weasel chewing through a cable down the road from your site, and that can shut you down for a few days. Oh, and then The Guardian had this article that came out with a nice pun, which is Large Hadron Collider on pause due to pine marten. Okay, so let's just whiz through some of the other things that are going on. If you have questions about this, you can ask me over dinner. So as I said, Alice is studying the very early universe, and the reason I want to flash a bunch of these is because you hear about the Higgs boson, and I've talked about the Higgs boson, but there are a bunch of other things that are going on at CERN as well. So Alice is doing the early universe. LHCb is looking at these exotic combinations, so you have different numbers of quarks inside of particles. So we have the pentaquarks, the tetraquarks showed here. Hold on. Yeah, and then the pentaquarks are not shown. I have to work out what the numbers, you know what I mean. Anyway, there's 4 here, and there's also 5, and possibly 6 as well. There's the antimatter factory that we have at CERN, which is my favorite named building on the site. It actually is called that. We have a banner on the front of the building. And this is where we create positrons and anti-hydrogen, antiprotons and positrons. We bring them together, we create antihydrogen, and we study their properties in various different situations. So we drop them to see if they get affected by gravity in the same way that matter is affected. We look at their spectral lines to see if the spectral lines are the same, because the spectral lines of hydrogen is one of the best known quantities that we've measured in physics, and so studying it for anti-hydrogen is a really interesting comparison. And so last year there was a really great announcement, although not so great if you're keen on anti-gravity, but a really great announcement that they'd measured the effect of gravity on antimatter for the very first time. Sadly, it looks like it falls at the same rate as matter does. And something from my own experiment, we had the first measurement of quantum entangled high energetic particles. So we've measured quantum entanglement in various situations, but never at relativistic energies, and this was the first time with top quarks in the ATLAS experiments, and it also opens up the LHC as a quantum factory in order to study these properties at relativistic energies as well. So, how does this affect you? So this is my summary now. My opinion is, learning more about our universe is a fundamental human curiosity, and I would do this job if we just got to learn some cool stuff about how the universe works. And that would be enough for me. I think it is a noble endeavor, the same way that we create art as humans, that we dance, that we have communities. We want to understand how our universe works. But there's also some cool tech that we get from doing this kind of work. So we have medical technology such as PET scanners. We have hadron therapy for cancer treatment, and we have various diagnostic machines that are not directly researched at CERN, but come from the technology that we either develop at CERN or that we drive to be developed through our research. So this is a broader physics motivation, but there's lots of medical technology that comes from our research. We have the technology to look inside of paintings, so there's historical information we can get as well. So you can use synchrotron radiation-based X-ray fluorescent elemental mapping in order to look inside of Van Gogh paintings and see, because he reused his canvases, so you can see what was underneath that canvas before he painted over it without destroying it, which is really interesting. We can look inside of pyramids without opening them up and potentially unleashing any curses. We can use muons to see if there are hidden chambers and also understand how they were constructed without having to damage them, which I think also culturally and historically is really important as well. So there's a whole bunch of other things, but these are just some of my favorite tech that comes from the work that we do in high energy physics. And then as we look towards the future, there's still a really long way to go. So really the aim of these slides is just to tell you that we've only collected about 7% of the data that the LHC intends to collect over its lifetime. We're hoping to run until about 2040, so there's plenty of opportunity in order to get involved and take part in this research and potentially be the one that discovers dark matter, because that would be very cool. We're doing lots of upgrades to the LHC before that time in order to have a more intense beam, which is then a big challenge for people like me who have to build the new detectors. But it's really a luxury problem when your accelerator is so powerful and producing so much data. And then there's a whole big discussion too that we can talk about over dinner of what's next after the LHC. And it's not decided yet. Right now, we have a number of different communities discussing potential colliders after the Large Hadron Collider. So do we build an even bigger circular collider? So this one's called the FCC. It's 91 kilometers in the proposal. Do we build a linear collider, which has some, each of these proposals have advantages and disadvantages compared to each other? Do we build a muon collider instead of electrons? Do we use a new research technique called plasma wake field generation? So these are things that are all being developed now, and we have to make a decision of where this field goes in the future. And speaking of the future, I'll just leave this up as we finish. There are a number of summer programs and internships you can apply to throughout your undergraduate program. And really what I want to leave you with is apply to everything you are interested in, because a number of these programs, sometimes it's just the luck of the draw. It means nothing if you're not selected. It's just that lots of people apply. And so really you should give yourself the very best opportunity that you can in order to have opportunities to try out research and meet people. So these are just a couple. I wanted to add a few more as well. There are more programs like the STFC Summer School in the United Kingdom and a bunch of other national ones around the world that I didn't list every single one. But yeah, thank you very much. Oh, sure. Yeah.
Okay. Right,
I could see you, so I was...
Yeah.
Yeah, no, it's fine.
Thank you again.
Thanks.
So since we have dinner immediately after this, we'll just defer questions until then, as you should have plenty of time to chat and ask away and make it more of a conversation style rather than a quick fire Q&A here. So just for dinner, first of all, we're going to get a group picture in front of the dining hall steps in front square. So if everyone can assemble themselves downstairs, then some of the Trinity volunteers will lead everyone down to front square by the steps. We'll take the picture and head in for dinner. It'll all be done no more than 10 minutes. So don't worry about it. We'll get yourselves downstairs and we'll get there. Bye.